right, let's get started. Nice to meet you guys. This is our first class for CSE 140. We're going to talk about digital circuits. A little bit about myself. My name is Leon Lee. I'm a fifth year, almost sixth-year PhD candidate in the Computer Science and Engineering department. I do research in hardware security, where I deal with these digital circuits in my daily life. And we have a team of TAs and tutors who are here to help you. Shreedip, that's our TA. He's a very experienced electrical engineer and verification engineer. So if you have any questions about designing circuits, verifying circuits, and you're looking for some industry opportunities, feel free to reach out to him. We have two wonderful tutors, Ted and Eddie. Ted has been tutoring with me for a while, and Eddie is new to our team. And these are like very friendly people, so feel free to reach out to us on Slack. Slack is going to be our main communication channel. We don't have a Piazza, we don't have a Canvas. All the communications will happen on Slack, including like announcements, just messages, or even group messages, discussion board, everything. Everything will happen on Slack. I already sent out an invitation last night. I hope you receive it. So just join our workspace whenever you get the chance. That's pretty much about me. And now I think it's time for me to get to know you. So I'll give you 2 minutes to think about these questions. What's your name, year, and major, and why are you here for CSE 140? And why is it in summer session 2? And what are your favorite topics, subjects, or hobbies in computer science or outside of computer science? Just anything. Right? Think about these questions for 2 minutes. And then I'm going to ask you to share it with some of the, the new friends that you're meeting in this class. Hello, hello. We're having an introduction right now. I just introduced myself. And now I want you to think about these questions. And then in like a minute or two, talk with your neighbors about them. Looks like everybody's ready. Yeah, maybe get into a group of 3, 4 people and then share with each other, why you're here, who you are, and things of those sorts. Yeah, feel free to move around and then come together. In general, the way we structure this class, there will be a lot of discussions, like maybe 2 or 3 discussions every session. So I would recommend you to sit sort of like next to each other if possible. Hello. How are you doing? Do you want to join the discussion and share, who you are with the rest of the students? You're good? All right. What's your name? Oh, I forgot. Forgot your face. All right. I hope you had a chance to talk with your new friends. Does anyone want to share with all of us who they are? Somebody from here? Anyone want to share? Yeah, just tell me your name and your year, or what makes you choose 140.
Ryan. I'm third year right now.
I see.
Yeah.
So taking this for like a major requirement.
Yeah, major.
I see. Anyone else from this side want to share? What about from here, middle of the class? Yeah. Yeah, many CE people. What about some other people? Yeah. Yeah. Okay. So, but who are CE majors? Yeah. Give me a hand for CE major. What about CS? What's your major? Marine biology. Then
I have the CS minor.
I see. So you're taking this more fun, like an elective, and yeah, it's good to know. Okay, welcome all of you to this class. And today's agenda is quite simple. We just said a human hello to each other. And I'm going to take you into a peek into digital systems from multiple angles. Whether you're interested in computer science, electrical engineering, or even just something that are sort of like unrelated, math, physics, management, economics, I hope that I can try to get you motivated into the next 5 weeks. And then also I'm going to briefly talk about the syllabus and some of these important details. So with that said, we're going to start our main discussion. And by the way, everything in this lecture are only for your curiosity. They will not appear in the exam. There's no technical question about any of these. So feel free to just relax and then sit back and then chill. This is a question for you. What comes to your mind when you hear about analog and digital signals? Any ideas? Yeah. What comes to your mind when you just hear about these two words? Yeah.
Like
Time? Like a clock. We have analog clock like this. Right? There are also digital ones that just display the numbers. This one, you see, essentially time is represented in a continuous fashion. Right? Can represent every little detail except that that glitchy second pointer. But in general, this is like a continuous signal, whereas in digital clock, it's like the pure number. Right? You cannot represent something like between this second and next second if you don't have enough digits. Any other ideas? Right? Like any audio files? Like musics and headphones. Well, I think if you do, people listen to analog music still, using those vinyl tapes. But more commonly, we're listening to digital music, and then they have this debate which one has higher quality, et cetera, et cetera. So really, the difference between analog and digital signal is how they represent time and represent value. Analog signal is continuous in time and continuous in value. Right? Think of it like a smooth curve that goes up and down, and it can represent any value within that range, from the bottom to the very top, without any predefined bucket levels. Whereas for digital signals, it comes from sampling the analog signal. It doesn't represent the full sequence of data, but rather we sample it every once in a while and then represent that data at our sampling point using several binary bits. And this process of converting the time from continuous to discrete is called sampling. I will take some samples every once in a while. And the process of converting that continuous data into some fixed width binary data is called quantization. And with sampling and quantization, we can convert analog into a digital signal. Here's a picture I grabbed from Amazon's website to advertise their high-quality audio. Right? They're saying, well, this is a standard which has a pretty low sampling rate. And if you pay for their premium, you can get this high-definition audio with much higher sampling rate. And for every sample point, they represent the data with more bits. Right? So if you represent every data with 1 bit, that's 2 different values. If you can represent every data with 10 bits, there are 1,024 different choices. And the more bits you put into that music representation, the more details you can capture. Right? You're able to tell apart those fine-grained details, differences between a high pitch and medium pitch and medium high pitch, etc. Right? With that, I'm going to show you one thing. You see my screen? OK, let me zoom it in a little bit. Sorry, Sorry, I'm trying to make a demonstration by sharing my main screen. Mirror the built-in display. All right. So here's a file size calculator I found online where you can input some of the data about your music and then find out how much that audio file takes, right? How much space. So based on Amazon's advertisement, they have this 1092 kilohertz sampling rate, which means at every second, they sample 192 times, right? So all the little details at every milliseconds can be differentiated with such a high sampling rate. They represent every data, right, at every sampling point with 24 bits. And then we typically have two channels, left and right. And if we plug in these numbers into this calculator, for streaming audio, it's going to take about 200 megabytes. That's way too much for any realistic storage purpose. Well, it might be fine for those real audio files where they have these 200, 300 megabyte audio files. But in general, this is just too big. And what they did is they ran some compression algorithm to, at very little loss, to convert that file into a smaller size so that it can be accommodated at a much more reasonable file size. Right? And this really tells us one thing about binary number. These binary numbers can be easily stored and transmitted. Right? Even with many bits, you can transmit them with high reliability. And that is an advantage of of digital signal that analog signal does not have. All right, any questions so far? All right. Yeah, again, for those who just came to the classroom, these are just for your curiosity. They will not appear on the exam, and there's no technical question about them. The next thing I want to introduce is CMOS. People sometimes feel intimidated by this idea, right? When they look into more of the physics stuff, particularly for computer science majors, they feel kind of intimidated. But CMOS, fundamentally, at least for the sake of this class, works in a very straightforward fashion. A transistor is built with polysilicon and the insulator, and some doped region and the metal and the body. And this body is controlled by a gate signal. And the only thing you need to understand this component is knowing that negative charge and positive charge attract each other. Right? That's for the sake of this class. And for this device, when you apply a positive charge from the gate, it's going to attract a lot of negative charge right below the insulator. And those regions of negative charge will form a channel between the source and drain, so they're kind of connected. Positive charge attracts negative charge, gets the source and drain connected. Right? So you can model it sort of like a switch. Right? You put down a positive charge, they're connected. Negative charge, they're disconnected. You can also think of this as a water pipe. You have a pump on one side, you have a drain on the other side, like a faucet on the other side, and it's controlled by a valve or gate. You turn the valve, water will flow. Actually, over here, current will flow through the device. If you turn off the gate, water will stop, and current will stop. Right? A very simple switch model of these MOS devices. And people actually built MOS in two different flavors. One of them is called NMOS, where you have to apply a high voltage to connect them. And the other one is like PMOS, where you apply a negative voltage to connect the source and drain. When you put these two devices together and you connect them to ground on one side and supply voltage on another side, you get a more complicated component that allows you to do a quite meaningful binary operation. And that is called inversion. So looking at this picture, if input is 1, we set NMOS, the one without the small bubble ahead of it. NMOS will connect, PMOS will disconnect. So output will be 0. Right? Will connect to the ground, which is represented arbitrarily as the symbol 0, a low voltage. Whereas if input is 0, NMOS will disconnect, PMOS will connect. So output is the same as your supply voltage. We just arbitrarily designate it as a logical 1. And in that situation, output is a 1 when input is 0. Right? You see, we're doing some inversion. Input is 1, output 0, input 0, output is 1. And this is really the foundation of digital circuits. You're able to do some manipulation with binary number in this, what we call the Boolean algebra. But we'll see more of that in the next lecture. Any questions so far? Or any thoughts? What do you think about these models? Feeling good? Feeling good so far? Right, you see, we didn't get too much into this physical and device design details, and that's really because the focus of CSE 140 happens at a higher abstraction level. So this is a typical way to model computer systems from like a very high-level application to a very low-level physical devices and the underlying manufacturing technology. The focus of CSE 140 is over here. It's above the device level. So when you move out of this lecture, you will not see anything about NMOS and PMOS. Right? You can learn that in probably like many EC classes. And we're not going to get much into computer architecture. That is more for CSE 141. And in this abstraction level, essentially, if you want to run an application, you can model it as an algorithm and write the code for the algorithm and send that algorithm. The algorithm is written in a particular programming language, which gets then sent to the operating system to be executed on a machine according to its internal instruction set architecture. That is the kind of language that the machine speaks. And after that, the real operation will be executed by a digital circuit. And this digital circuit is what we're learning here in CSE 140, ranging all the way from how to convert some behavioral circuit description into an implementation, and also being able to go back and forth between these abstraction levels by making both engineering and reverse engineering happen. Engineering is essentially implementation. I give you a specification, you implement it. Analysis or reverse engineering is going the opposite way. I give you a circuit, you tell me what it does. And those are the two main learning objectives for this class. All right. And modern computing is a lot more complex. This is only the most naive computer system where everything flows in one direction. But computer systems are a lot more complex nowadays. You don't have to go through this order anymore. In fact, any computation can be implemented in software, in a particular programming language, or in hardware. I'm talking about any algorithm. So anything you can think about, there's a software implementation, of course, and there's a hardware implementation as well. And depending on what you need, right, whether you're prioritizing flexibility or performance or power, you might make a different trade-off between software implementation and hardware implementation. And so, of course, software is very easy to implement, easy to execute, but hardware is a lot more efficient. And in general, if you implement an algorithm in hardware, you get about 100 times to 1,000 times better in energy. That's just because we are skipping all these translation layers in between. We're going directly from an application or algorithm into the hardware implementation. And it is for that reason that people nowadays are designing a lot of accelerators for some specialized purposes. Right? Computer chip or CPU is like a general purpose processor. And you have like GPU, graphics card. Right? You have like AI chips, neural engines. Right? Those are like specialized hardware. And those are in our chip because they offer much better energy and performance. And the other thing is increasingly, even for software people, they are making use of hardware devices for their software execution. There are convenient tools that allow you to map any software into a few programmable devices. So this is like a reconfigurable hardware device that offers much better performance than CPU, but not as good as application-specific chip. But for software people, it's kind of easy to use. So they merge some of these hardware components in their software implementation flow to create a hybrid system for better performance, better energy. Right? So the next question is, if you want to design a piece of hardware, right? Suppose we're doing this from scratch. What do you optimize for when designing this hardware? Right? What are some of your considerations? I think for software people, consideration would be performance, readability, modularity. But what do you think are some considerations for hardware? I'll let you think about this question for 1 minute, and then take some of your inputs. Just in general, if you want to run some computation on a piece of hardware, what do you optimize for? There's no right and wrong answer. Just do a bit of brainstorming and get the conversation moving. I'll give you 1 minute. And feel free to talk with your neighbors. look at some of your inputs. What do you think? Just any thoughts?
Efficiency.
Efficiency?
Like power efficiency.
Power efficiency. What do you think that's important for hardware design?
It's sort of like not having like excess loss of power, like current.
Mm-hmm.
Yeah.
Yeah, and particularly nowadays we have these mobile devices that run on battery. Right? So energy is becoming more and more important, and it's actually becoming the number one design consideration when designing hardware. It's no longer performance or area; it is actually power. Any other thoughts? Yeah.
Just like performance.
Performance. Yeah, performance is still important.
Like how fast it'll take you to do a specific action.
Yeah. How long does it take for you to execute some operation? Performance is always important, and especially in this competitive marketplace, where people compete on performance. Right? And for most of the consumers, they look for performance when making the purchasing decisions. So that's definitely another important consideration. Any other thoughts? Sorry, what's her name?
Judy.
Judy?
Judy.
Judy, I think.
Like space, or like how much space the hardware would take.
Yeah, why do you think that's important?
Because I guess like the smaller you can get like something, the more you could use and the more like
Exactly. Area is very important, how big the chip is. And I think that's important for two different reasons. Number one, the smaller the chip is, the cheaper it is to manufacture it. Second reason would be, well, we also have like size limitation on these mobile devices. Right? Think about some of those AI glasses. They need a tiny chip to fit into the frame. So size is important for cost effectiveness and also like real space constraints. Any other thoughts? Right? This is not really a hardware question. It's more like a general engineering question. Share with us what are some important considerations for optimizing hardware in your experience? Yeah. So other than area, power, delay, what are some other important considerations?
Those are the main.
Those are the main. Yeah. Indeed. Yeah. Area, delay, power, these are the main considerations. They can be written in short as ADP, area, delay, power. And that's what people talk about in the industry when establishing the baseline performance of a chip, right? And also setting the design goal. All right. And I want to introduce you one particular architecture for hardware. It's called von Neumann architecture. Von Neumann architecture is, of course, created by John von Neumann, which is the pioneer of, I don't know, like pioneer of computers. So in his view, right, every computing device can be modeled in this fashion, where there's some inputs and there's some outputs. And inside this computing device, we have some control unit to determine the kind of sequence of some operations. We have a arithmetic logic unit. Those are like doing the real logical operators like AND or XOR, or arithmetic operations, addition, subtraction, multiplication. And with these operations, you can actually model any problem. And there will also be some registers. So registers are essentially a storage device. They allow you to save some data and then make use of them a bit later. Right? And register will sometimes communicate with the memory unit. Memory is essentially a larger and slower register. It's a larger and slower memory device. If you need a lot of data, they just cannot fit into registers. You better put them into a larger memory. Right? And this is essentially our baseline for the class. We're going to see how we implement many of these components, particularly the control unit, arithmetic logic unit, and towards the end of the quarter, a bit of registers and also this high-level picture. How do you implement this complete data path for computation and control path for controlling the sequence of operations to realize complicated functionalities? And we're talking about the area of a chip. And these are like physical chips. Right? It's not a piece of software where you can easily disseminate and then compile. It is a chip that you need to fabricate. And this fabrication process is super expensive and super complicated. Typically, a chip goes through these several stages in its design and manufacturing flow. We first, a bunch of hardware engineers they wrote the code for those hardware. Right? Hardware has their own languages. Those are called hardware description language. Essentially, just like a language, but for hardware. And this language has some special features to allow for parallel execution. That's another distinguishing feature of hardware, where things happen in parallel. Like all of these gates, all of these components, they can be evaluated in parallel. And then we'll send it for fabrication or manufacturing, which is the process of putting those transistors on a substrate and then etching out all the gates, all the metal wires to actually realize this hardware chip. And after that, this chip will be put into a product, right? It will be put onto a board. The board will be put onto a larger board into a cell phone, right? Or a PC, whatever. So all of these components will come together eventually to build a complete digital system. We're just talking about power. We're just talking about area. And areas is important because there's some manufacturing defects in that manufacturing process. Manufacturing is not perfect, right? Even this tiny piece of dust, right, in this ultra clean room could still happen, and that will have a detrimental effect on the usefulness of a manufactured chip. So this is like how the chip gets manufactured. They first get manufactured like in a kind of cylinder of silicon substrate, and then we cut out a piece and then put these individual chips onto that roundish wafer. Depending on the size of, suppose we have some defects, right? Some of these red dots, they represent manufacturing defects, and any chip impacted by those red dots will become malfunctioning. With the same defect distribution, right, or same defect density and distribution, the bigger you make your chip, it is more likely for them to be impacted by any one of these defects. This is another reason why you want to keep them smaller, to make sure that your good rate is called yield. Your yield is high. And at the beginning of a new manufacturing technology, that's 3 nanometer, right? And that's like the state of the art right now. At the beginning, the yield is roughly 20 to 30%, which is super low, right? 1 out of every 5 chip is functioning correctly, and all of the others are just malfunctioning. You need to throw them away. There's no rescue. But towards the end of a manufacturing technology, as it's getting more mature and people have time to refine the technology, we can get about 80 to 90%. Or for some of the ultra old technology, like 150 nanometer, you can get near perfect manufacturing. Right? But in general, it's very hard to get good chips. And therefore, we need to do some testing after we manufacture the chip. Right? You do some testing for software. You write your code. You need to run some unit tests. For hardware, testing still needs to happen, but it happens at many stages. At the design time, right, when someone wrote the code for the hardware description language, they need to verify that it's working properly. When people manufacture the chip, and for each individual manufactured chip, they need to run some additional testing to make sure that the manufacturing process is perfect. So that is costing a lot of money, and testing or this reliability is also becoming an quite important consideration when designing hardware products. So here is just a very incomplete list of concerns that people put into their chip design process. We care about performance, cost, right? And those are like area, delay, and power. We care about whether this is a general purpose device or whether this is a specialized device. They will put towards different market segments for different applications. Market needs, right? What is trending? What are consumers looking for? That's, of course, an important consideration. Reliability, security, and trust. Right? We are operating in this distributed supply chain. Chip design companies, they sit in the United States. But this chip gets fabricated in Asia, right? Taiwan, Korea, those are like the 2 largest manufacturing places. Right? And then testing and packaging is actually done in other countries. Right? It could be done like in China, India. And eventually, they will be sent back to consumers all over the world. So there's a lot of security concerns. Your chip design is going through many hands, right? To make sure that it remains private, it remains secret, right? And there's no compromise, no Trojan in the hardware sense. So really a lot of design considerations. But are we going to deal with them in this class? Probably not. Each one of these topics is one graduate level class. We have an EC class just talking about hardware security, right? We have some EC classes talking about how to optimize for area, delay, and power using industry tools. And this is like an introduction to digital circuits. And it's actually mostly tailored for computer science people. I mean, we focus a lot on the algorithm and the abstraction levels of the underlying process, rather than the kind of these real design projects. Right? Any questions so far? Are you more or less feeling comfortable about what we're about to cover in this class? All right. If not, I'm going to move on to the next part of today's presentation, where I will show you a little bit what you will see for the next 5 weeks in like 30 minutes, right? Just to give you an overview about what we're about to cover. We're going to do some number representation, how to represent numbers in a digital format. And if we go back, this is like 35,000 or 37,000 years later. That's how people do counting, right? They take a piece of bone, and then they cut some of these edges, right? They cut some of these notches on the bone. And that is a way of doing counting. And do you know what is the base for that kind of counting method? I mean, in our daily life, we're dealing with base 10 decimal, right? What is the base for that? That's base 1. Right? Like every notch represents a magnitude of 1. Right? That's base 1. And another way to do counting is with this tally mark. Right? It's essentially similar to that, but you can group together every 5 tally marks into a group, which makes it a little bit easier to visualize. And people have been doing tally marks all over the world in different ways. This is probably the kind of European-American way of doing it. From your cultural backgrounds, I know people come from all over the world. How do you represent this kind of counting using tally marks in your culture? Do you have for those of you, who have some knowledge about other countries of their culture and history, do you know how they do counting? Different shape. Could you show us that shape over on the board?
Sure.
Yeah. Yeah, just come over here, and yeah, maybe just show it to us how, where you're from.
Taiwan.
Taiwan, I see.
It's like this for 5.
Yeah, it's a different letter. And could you also break it down into like 1, 2, 4, like at each step, how do you do it? So 1, 2, 3. I see. Yeah. I'm from China. That's also how we do counting. Anyone else want to share with us how they do counting? Is it like, one of these two? More or less. I think for some European countries, they do this kind of square with a slash across the diagonal, right? But the same idea, just like 5 strokes. This is like a letter, a character in Chinese, which means like straight. And it's like very squarish, so it's kind of easy to like visualize. And I think similar goes for that, American tally mark. Right? They're really the same concept. And as time evolves, we also have different ways, like the more advanced ways of representing numbers. You need to put down a lot of strokes if you want to count a big number. Right? It's just not a scalable method. So people start to develop some more, should I call them creative methods? Right? Like these Roman literals. What they do is they have like a different symbol for each magnitude, right? 1 and 5 and 10, like they have different symbols. So instead of writing 5 strokes, you can just write a single character to represent 5. Or even some of those bigger numbers, they have their own representations. Any ideas why this one is not prevailing in the current world? Some of these questions I'm throwing at you, I don't have an answer. I'm just trying to get some of your insights. Do you know why this is not the common way that people do number representation nowadays? Yeah. There are only so many letters. Yeah. Well, I think they have letters for some very big numbers, but just putting down more like under bars or over bars. I don't know. But the bigger you want to represent your number, the more numerals and characters you need to create. right? And that is a lot of memorization overhead. I think. I think in the Roman time, for like a normal civilian, they don't know all these numbers. They can only do like simple counting. Once you get over 1,000, it's kind of hard to memorize and hard to use. Any other ideas? Right, one of them is this bottleneck of needing new literals for larger numbers. Right? What are some other issues with this representational system? All right, I think the other issue is it's not that compact. It's not better than 10 marks, but to represent some number, this is like a number less than 2,000. You need to write down many literals, right? So not work, not as easy as the regular Roman. Like Arabic. I think it's called like Arabic numerals, right? The regular base 10 numerals. So this number I'm putting over here is actually some letter M, that's 1,000, D is 500, CCC is 300, and the L is 50, 3x is 80. So 8, this is 9, so that's 1889, right? 1,889. And this is like that comes from like on one of these buildings, right? Must be the year it gets built. All right. With Arabic numerals, you can represent that number in a much shorter format. Like there are like 4 digits over here rather than those like 10 different numerals. It's kind of easy to remember. So if you think back to how we learned these numbers when we were like very young kids before elementary school, we just remembered the 10 different symbols from 0 to 9. That's something we have to memorize. You take it for granted, but something that we memorize at some point. But after that, once we learn those 9 literals, that's the only thing we need to learn. You can just order them in different orders, in different sequences, to represent different numbers. If you want a larger number, you just put more of them, right, with more digits. And this is actually the concept called positional number systems. By putting down the same literal at different positions, they represent different magnitude. And that is something that does not exist over here. It's something that does not exist in the Roman numerals. Right? This is a feature that is unique to Arabic numerals. And I think this was actually an invention at the time when that literal system was invented. All right, so this is for decimal, and you of course know how to interpret this number, 1,889. Right? I don't have to teach you this. We're gonna just relearn everything in binary, of course. That's a language that computer speaks. Right? In binary, how do you represent numbers, and how do you actually convert between different bases? And there's actually a lot more that we need to learn about binary, how to do counting, how to do some simple arithmetic operations like addition and subtraction, how to do more complicated operations, multiplication and division in binary, how to represent fractional numbers, right, like decimal parts of numbers, and also how to represent negative numbers, how to do conversion between this base to another base, between for both the integer and decimal parts, and also how to represent sometimes ratio and exponents. And these are some of the things we'll see in week 1. Number representation together with some basic operations. Yeah. Any questions so far? All right. And the next topic is about error detection and correction. And you see, manufacturing is not perfect. And there are, of course, more imperfect things in our life. One of them is communication. Right? Like what I'm saying right now may not be received at 100% accuracy when it reaches your ears, especially for those people who are watching recordings. It's going to lose even more information. But in general, even if you transmit digital data, it's going to lose some information here and there. It could be during storage. It could be during transmission. It could be impacted by some errors, or even by some active attacks. Right? Attackers could hijack your communication channel and inject some very dangerous data. So what do people do is we need to use some way to be able to detect and correct errors for these binary numbers. Oh, sorry guys. So this morning I was shopping on Best Buy, and then I found a very good deal on an Intel processor, and the deal ends at 12, and I forgot to place the order. Is it okay if I do it right now? I'll get back to it actually in 2 minutes. Oh, actually, here's one thing I want to show you, since I'm already on this page. All right. So I'm looking for this 14th generation Intel processor. It's probably not the best, and Intel recently has a breach, some manufacturing defect. They refuse to recall on some of these newer processors. But this processor has 20 cores and 28 threads. Does anybody know what that means? 20 cores and 28 threads. Yeah, different processing channels, exactly. Right? Like these are 28 different channels that you can use to process different computations, and they can happen simultaneously. But this idea of having more threads than cores, essentially using some of the cores for multiple threads, is called multi-threading. It's invented by one of our professors in the CSE department, Professor Dean Towson. And I have him very nicely as a sticker on my cell phone case. So this is Professor Dean Towson. He's one of the inventors for this multi-threading, right, to allow us to greatly scale our computational power. Sometimes double, sometimes a little bit less than double. But we're getting more out of our budgets. All right. OK, I'll get back to lecture in 1 second. And this is my email. Feel free to shoot me an email for anything. Or what?
Is that on discount?
Yep.
I think Amazon is cheaper.
Oh, really? Oh, thank you. OK. But I think I ran into some other issues. My credit card number is incorrect. So I just entered this number, and the web page told me that it's incorrect. What do you think is happening over here?
Background check in the.
You think it's checking a database? That's a good guess, actually. Right? Maybe they have a database of all the valid credit card numbers. But that's quite expensive, right? Think about like all these billions to trillions of transactions that are happening every day. Just too much to check. And every day people are issuing, like banks are issuing new credit cards. And how to keep this database up to date, that's a tremendous task. And it's a lot of communication and computation overhead. It's probably not a database. So anyone can take a guess of what's happening. How did they know that my credit card number is incorrect? Yeah.
It's just a guess, but like maybe because there's like a pattern or like a way. Or it goes through.
Yeah.
For example, like if you put a 4
Mm-hmm. Yeah. Yeah, there's certain rules to these credit card numbers, right? 4 is like a Visa. 37 is actually 37, 38, 39 are American Express. What about MasterCard? I'm quite into this. I look a lot into this credit card industry. I think that there are a lot of like interesting financial stories and then opportunities. If you try to get points and redeem them for free travels. But your guess is correct. There's some algorithm underlying these numbers to check for its correctness. And the last digit is actually called the checksum bit. Checksum, check the summation of all the other bits, essentially, right? But not the straight summation is through a particular algorithm, but it's a way to embed some additional bits to make sure that whenever you made a 1-bit typo or 1-digit typo, it is not recognized as the correct number. And the incorrectness actually happens over here. It's not 2022, it's 2024, right? So if I change it to 2024, it does work. And this is one of my credit card numbers, but an expired one, and then closed account. So don't worry about me. What I'm just trying to show is that data correction and error detection and correction is happening every day, right? For many of these, whenever you need to communicate some data with other people, you better check for accuracy, right? And this is called error detection. It tells me that I made a typo, but it cannot correct it for me. All right. Do you think I'm actually going to buy, like, I'm going to actually buy something during lectures? All right. So data error detection and correction is everywhere. I just show you how to do that, or how that website does it for a credit card number. You can actually also do sort of like an error correction for QR code. Like I put this smudge. Like think of this as a coffee spill or some, very very old piece of paper that's not clear anymore. But I think you can still scan it, right? Maybe try it out. See if with your cell phone, can you scan this QR code and then get some reasonable data out of it. Does it work? No, it doesn't work. All right. Maybe this smudge is too big. I'm going to move it to the side a little bit. What about this? It's working for me, I think. Does it work for you? Yeah, maybe you have to go through a little bit of trouble, right, because of that smudge. But eventually it will work, right? And this is an example of error correction, where you can not only tell that something has gone wrong. Of course, you can see it has gone wrong, but you can also correct the error and make the actual computation happen. And that's actually your, the quiz for your day one. Well, you don't have to do it right now. It's not a in-class quiz. This is like a survey that I want to collect after the lecture to learn more about you. And then we'll take those information into consideration for the future planning of the course. All right? But do you think, OK, so we have an example of error detection, an example of error correction. Do you think we can apply error correction to credit card numbers? And let's say for the Best Buy website. Do you want it to do error correction for you? You want? You don't want? OK, why do you want to do error correction? Why do you think they should do error correction for your credit card number?
In case you accidentally type in someone else's credit card number and then use their account.
Yeah, that's a possibility. Why do you think we should not do error correction for credit card?
Because error correction would mean that they could misidentify the number you put in.
Yeah, exactly. But they could misidentify and then correct it in the wrong way, right? Let's say you made a 2-digit error, then suddenly it's corrected to someone else's credit card numbers. That would be a disaster, right? So we really don't only want error detection to give you a sign that something has gone wrong, and then you should do that manual checking to make sure that you type your number correctly, right? That's pretty much everything for week one. We're going to see some of the number stuff in the binary world. Essentially in binary, how we do error correction and detection also. And then we're going to move on to Boolean algebra. Boolean algebra is fundamentally how digital circuits think about all the operations. All of the logic gates, you have heard about AND operation, OR operation, XOR operation. Those are essentially Boolean operators. And between these two expressions or these two equations, which one is correct? I mean, in the normal algebra, right? The ordinary algebra, which one is correct? Top one? Yeah, the top one is correct. Bottom one is incorrect, right? Multiplication can be distributed into addition, right? But not the other way around. In Boolean algebra, both of them are correct. And that is what's creating some of the confusions in our mind. You really have to get comfortable with the way Boolean algebra works before you can design circuits. And this is, the beginning of week two, we're going to see how Booleans, how to think about this new algebra, a new way of adding together numbers. And actually, the space of the number is quite limited. It's only 0 and 1. Right? But within those 0 and 1, and essentially you can think of this as having a modular operation, then the bottom one would also work. All right. And with Boolean algebra, we're going to design two kinds of circuits. One of them is called combinational circuit. The other is called sequential circuit. Combinational, as the name implies, is just taking some combinations of your inputs. At every time, the computation depends on only the current inputs. You change the input, the computation will change and produce different outputs. You change it to a different input, new computation, give you the output. It has no way of memorizing what you have done before. Right? At any moment, it's only checking the current inputs to produce the current outputs. Sequential circuits has additionally some memory. And this memory allows you to remember what you have done before, and then bring that knowledge into future computations. With combinational circuit, the capability is very limited. 2 to the power of input bits. That's all the computations you can do. Right? But let's say think of our general purpose computer, and they can do a lot more computation than what we can imagine. They can actually do unlimited number of computation types. And that is only enabled by having some additional storage elements to be able to expand your computational power, not only by putting down more inputs, but also by expanding on the time domain. Right? By spending more times and then remembering some of what you have computed, eventually you're able to tremendously expand your computational power. And week 2 and 3, we're going to focus on combinational circuits. Week 4 and 5, we're going to focus on sequential circuits. Right? So, but essentially, many of these combinational knowledge are essential for designing sequential circuit, because sequential circuit also has a combinational component. Right? So we're going to learn combinational circuit first before moving on to sequential circuits. And for the sequential circuit part, we're going to see how do you design these memory components, and how do you realize some computation that are sequential in nature in a circuit format. All right. And in this class, you're going to see a lot of algorithms. Like, after all, this is a CSE class, so we're going to focus slightly more on the algorithm side of digital design rather than the implementation side. We're going to see some logic minimization algorithm. Right? So we're not just trying to design and implement a combinational circuit and sequential circuit, but also trying to optimize them to get the smallest circuit so that they have like the smallest power consumption, the smallest area footprint, and all of those nice features that we're looking for, again, in this competitive marketplace. We're going to see some of the classical algorithms for solving graph-related things or set-related things, and those can also be used for the same logic minimization and optimization problem. And some of these algorithms are unique to sequential circuit modeling, and then we're going to talk more about them as the quarter progresses and then when we get there. Yeah. Does this set you a good expectation about what to expect in the coming several weeks? Right. Again, to recap, week 1 is about numbers, about binary numbers. Week 2 is Boolean algebra, and then we're going to spend the rest of week 2 and week 3 on designing, analyzing, and optimizing combinational circuits. And after that, we're going to move on to sequential component design, and then sequential circuit design, analysis, and optimization. All right, again, CSE 140 is about the algorithms, applications, analysis, and theory of digital design. And we're going to cover all of those aspects. Concept mapping, again, essentially just a recap of what I just said. Number, combinational, sequential, and towards the end, we're going to do some system design to be able to connect all of this knowledge you have gained in the class to realize much more complicated and scalable computations. Right? System design is essentially the part where we have those registers, the data paths, the control unit, and all of them gel together to realize complicated operations. Here are the learning objectives of this course. And this is something I want to really elaborate. It's a little bit different from many other classes. On one side, of course, we want to learn essentially the core materials of CSE 140, digital design. We're going to see how the binary, combinational, sequential, Boolean, and optimization design principles, how those kind of technical things work. But I have more learning objectives for you. I want you to eventually develop some better engineering skills and a stronger engineering mindset. And that's where I try to formulate over there as some of the abstract learning objectives, where I want you to be able to consider real-life problems. And in the lecture, we're going to go through many real-life examples, not necessarily related to chip design, but just in general, to broaden your scope of knowledge. We're going to apply math and science to solve not just the existing problems, but also new problems, right? To be able to apply what you have learned into solving novel challenges. We're going to try to envision multiple solutions and explore the trade-off. Right? Oftentimes, you have a choice. For many of the engineering tasks, you have a choice, and you need to make some decision. Power, area, delay, those can be traded off. To solve logic minimization, you'll see 4 and 5 different tools, and that is a trade-off, depending on what you want. Is it a computer algorithm? Is it doing it by hand? Is the expression complex or simple? You need to make that choice. I want that to happen. I want you to be able to make that decision by yourself and hopefully find, for any kind of problem, any kind of challenge, a new way of thinking about it based on what you have already learned, and then pick the best set of tools from your arsenals to better solve it. All right, and we're going to also allow teamwork on the workbook, which is our main evaluation method, and I'll get to it in 1 second. Class modality. So, of course, we're here in the lecture, and there's no discussion section for today. Discussion section starts on Wednesday. But every time we meet 4 times a week, Monday to Thursday, and I know that's a very busy schedule. That's really the nature of a summer session. Everything happens at a super accelerated pace. And there's no required attendance. There's no point associated with attendance. But I hope you to attend, and that is really what I expect from you. This is an in-person class, not a hybrid, not a remote. But I think we're already in the upper division. I don't want to enforce any policy for that kind of attendance. Discussion section is in person and optional, and all of this will be recorded via podcast. But I think that's more for your review purpose rather than relying solely on those channels. Office hours will be a mix of in-person, hybrid, and Zoom, and we'll post the schedules on Canvas. We have an embedded calendar over there where you can just see all the information, where it happens, what modality, and who is holding the office hour. More support, Slack. So this is our main and only communication channel. Everything, message, discussion, whatever announcement, they will happen in Slack. And you can also create your own Slack groups if you want to invite a few friends to join some discussion, and then we can now see your discussion. So it's perfectly private. Here's how we're going to grade you. 60% workbook. Think of this as a homework for now. I'll get back to it in 1 second. 6% homework workbook, and then 40% exam. And 2 exams. One of them is a midterm, happens at the beginning of week 3. The other is the final. And you also have a chance to make a presentation or do a project of your choice. You can freely choose your topic, whatever you like. And do that presentation, you get 2% extra credit. All right. So now I'm going to go through each of them one by one. So the workbook. Can you all access Canvas already? Yeah. So every day before lecture, I'll publish my preview lecture slides and the workbook on Canvas. And the workbook is, essentially consists of 4 components. A review of what happened today, right, for you to just get a recap of the learning objectives for that lecture. I'll tell you what you need to prepare for the next lecture. Essentially, a few open-ended questions for you to research. You can do this research in whatever way you like. You can read our textbook, which is pretty nice, but it's a little bit mathematics heavy. You can do some online search, Google, GPT, watch a few YouTube videos, whatever you like. Just make sure to do a bit of preparation before coming into the next lecture. And then we have these questions. These are the questions that you need to submit, and you will be graded on. We have foundational practice, which is like the kind of basic questions, and also creative practice, which goes a little bit outside of the box to motivate you to think critically and creatively. All right, and you can see an example of this from today's lecture on the course website. But this is not really a representative example. Wait until tomorrow when we have some technical contents to see what this format looks like. All right. And again, considering the fast pace of the summer session, I'm afraid that we have a pretty fast coming deadline. So weekdays, I mean Monday to Wednesday, right, during weekdays. It's going to be a short workbook, 4, 5, 6 questions. And then submit them in 2 days by 11 a.m. So today's workbook, submit them by Wednesday before lecture. Tuesdays by Thursday before lecture. Wednesday by Friday. And weekend workbook is a little bit longer, and that will be released on Thursday, the last lecture of the week. And then you have until next Monday to make the submission. And these questions will be graded on a mix of correctness and completion criteria. But we'll not tell you in advance which one is on which criteria. So I really want you to put down your best effort to all the questions. And this is really where I think learning happens and where most of you will be evaluated on. Right, 60%, that's a vast majority part of your grades. So do this workbook, try to develop a proficiency in the material, get all the help you need, discussion, office hours, Slack chat, whatever you need, and then try to get all of these points. And then check the syllabus for late policy. We have a very lenient late policy. Essentially, you can submit the weekday workbook, with a 3 to 5 day extension at only 5-point loss. Weekend workbook is like 2-day extension with 10-point loss, so 1% out of that 6%. Right? In this class, you have essentially 1,000 points in total, and every 10 points correspond to 1% of your course grade. Right? So at a pretty minimal loss, you can submit them late, but I really encourage you to not do it, because more lectures are coming. I want these workbooks to be a place for you to just settle down and absorb, convert what you have listened into some short-term and long-term memory, and be able to carry that skill over to the coming lectures. Right? So I really recommend you to do it on time, but you will not be penalized much if you have to be late every once in a while. All right, and this is what I think how learning happens in this class. Pre-class preparation and lecture, they'll probably together form half of your learning. And some people do this preparation different ways. They like to save it until after the lecture, which is perfectly fine. But I mean, your preparation and the lecture is half of where you learn, and the other half is these exercises. And the exercise by themselves do not allow learning. It has to go through this learning loop to be able to kind of receive the feedback, get to see the solutions and the explanations, and be able to find out where you missed out on any specific topic. So we're going to provide plenty of supports to make this happen. We'll release the solution on Gradescope after you have done the submission and we have already graded your work. And then you can reach out to support before, after, whenever you like. And I'm just here to provide you the support. I really want you to take the initiative for your own learning to make this feedback happen. And that is essential coming to the midterm and final exam, which historically have been quite challenging. So extra credit project. I think some people are curious about this when they say extra credit project. They want to ask, what do I need to do? And the question is, you can really do anything. Do anything that connects any topic with your experience in class. Right? I don't mean connect them with technical concepts. I mean with anything experience from your discussion. If you want to talk about how you interacted with your classmates in lecture, you want to talk about how do you feel about the course design, whatever you like. Right? Anything you experience in class with your personal interests. Here are some examples. You can write a history report on computation, on CPU, GPU. You could talk about a recent chip security breach, when that happened, why that happened, and how did people fix it. You can do some coding project to design a piece of hardware. You can just report on pretty much anything you like. There's like a very free, open-ended extra credit project. Sorry. I think this is just a way to keep you motivated. Throughout the quarter, always keep in mind what is your interest and how you can bring the knowledge you gain from this class to that of your personal interest. Right? People may not be interested in digital circuits, and that's perfectly fine. But I think there's some engineering skills, some critical thinking skills that people can all benefit from the class. And this summer is actually my first time as an instructor, and I just finished summer session 1 for CSE 140. And I want to share with you some of what those students did just a couple of days ago. One guy, he built a 4-bit binary adder in Minecraft using Rhinestone. He actually built a lot of other gates that's on the other side of the screen, which I'm not showing. Another girl, she tried to teach a 4-year-old about binary numbers. And then she reported her teaching methodology, her course plan, which is very interesting. Another girl, she built an RPG game related to binary puzzles. And then you can solve a few puzzles to go through multiple scenes and eventually reach the final boss. And other people have also done some reports on all kinds of things. I just cannot imagine beforehand. They reported on the evolution of digital circuits, graphics card. They report on the impact of immigrants on the US semiconductor industry, which is kind of interesting. And I did learn something from it. The history of chess computers analyze DNA sequence with finite state machines. Finite state machine is one of these sequential models that we'll see in week 4 and 5. And finally, some people implemented the algorithms that we learned in class in a computer software format. And they're able to essentially automate that process, and which are pretty cool. I think these are like very cool ideas. But feel free to bring your own idea onto the table. And I'll let you know more about the kind of format, the grading criteria for that project a bit later in the course. All right. There's just one thing I want to remind you is to choose integrity. We have 6% on the workbook. And those are, of course, not examined, not timed, not proctored. And I expect you to, again, take the ownership of what you did, and take a leadership in your learning. Right? I put full trust on you. And please also, pay me back with respect. So integrity I would say, consists of 4 components: honesty, and be honest about what you did. Always be transparent. If you cited anything from your actual credit project, please specify it. Right? And any work that you did should be your own original work. Trust. I trust that you will take responsibility for academic integrity. I hope that you also trust me in giving you fair assessment, and then making sure that our grading and all of the contents and questions are also fair in nature. Respect and responsibility. Yeah. All right. Be responsible to yourself. And then, of course, I will try to take everybody's voice as an important message, and then accommodate as many things as I can. All right. So to sum it up, these are the keywords that I think will happen in this class. Integrity, support, and transparency. I'll be transparent as much as possible, by telling you exactly what you need to know. Before the exam, I'll tell you what are the questions. Not the questions, what are the topics for those questions, for each and every question that will appear in the midterm and final exam. And we're here to support you. That is our main goal and my main function. And me, TA, tutors, we're all here to support you, and we'll provide plenty of support channels, both in those scheduled office hours and also through Slack. I hope that we can create a diversity, inclusion, and equity environment. When we have these discussions, try to get more people involved and get their voice heard. And I want to remind you that this is not an easy class. I'm trying to uphold a pretty high academic level. So I do expect you to put down your best efforts, and I think everybody can succeed. And historically, people from all kinds of backgrounds and all kinds of academic levels, they do very well in the class. Right. With that said, that's everything I'm about to say for today. And please complete this day 1 survey right now, or after you leave the class, whenever you like. I just want to collect some data so that I can design different accommodations based on your needs. All right. I think. Yeah, just do the survey, and when you finish the survey, feel free to leave. That's everything for today. And of course, if you need more time to work on this, you can also do it offline. It's on your workbook for day 1. There's a link, QR code, they're all over there. So do it whenever you like. Yeah, if anyone has any questions, feel free to just come to the front, and then we can talk. thank you guys for coming. I look forward to seeing you more in the future.
Thank you.
How is your summer going? What is the session? My tutor was Omar. Omar took EC. Omar was taking EC 101. He said you are a very nice TA. Yeah. How do you feel about the lecture? Good. Yeah. Try to keep it fun. And we'll meet at 1. Okay. It was pretty good. Yeah, very busy. Second session is not better because I have all these things ready. So probably an easier life for me. But it was good. Yeah, teaching feels good.